Thank you very much. I think you can hear me.
Yes.
Perfect. Okay. So thank you very much for the invitation and the warm welcome. And I'm pleased to speak here in front of such a skilled audience. I have learned a lot today. And today I will put the two main topics of this workshop, namely V2X and IoT in the context of 5G security. That means that we will see security challenges that arising from putting those topics to 5G as a foundation, as communication layer. So I got already my introduction, so we will skip that. So 5G opens many new opportunities for us. For starters, I will go here over three important examples. In critical infrastructure, 5G is used as communication network, for example, in the interaction of sensor networks, in power supplies, and so on. With new possibilities of campus networks, and we will later go on to this more in detail, 5G forms the basis of smart factories, and here too networking changes, for example, the production cycle of your factory. And the third area is the integration of 5G into road traffic. Through communication between cars, important information can be exchanged in a timely manner. And this, of course, helps to optimize. We have seen this today in the morning, and optimize the traffic and reduce the number of accidents. These applications areas are diverse and bring their own unique requirements in regards of security with it, but they will have all one common thing. They are an integral part of our daily lives. However, this pervasiveness and the fact that we rely so much on 5G also carries a huge risk, which we all know about. If something goes wrong, so for example, if a security problem arises, the consequences are fatal. So at a first glance, it is quite simple. Yeah, we need to secure the networks, but the question is how, and in particular, we need to ask ourselves how in particular of those specific topics. So 5G means that we have already 3 mobile network generations before 5G. We will leave 1G out because analog technique is not our main purpose here. So every 10 years, a new generation of mobile network, mobile communication system is released by the 3GPP to meet new requirement. While the focus of 2G was mainly on telephony and text messages, 3G focuses on data transmission and 5G now focuses on connecting devices. If we look at the previous generation in terms of their security properties, we quickly see that all generations have extensive security flaws. For example, 2G allows eavesdropping of phone calls and data connection due to encryption algorithms that were weakened by intelligence services. 3G brings a significant improvement in regards of those algorithms, but still rely on an insecure interconnection or core network protocol called SS7, still responsible for major attack vectors in the mobile networks industry. And 5G misses important security features such as integrity protection for user data. So the question for now is, what does 5G do better in terms of security in regards of the new applications, in our case, V2X and IoT? To illustrate the life cycle of a mobile network and where the security vulnerabilities can occur, we first have a look at this small life cycle or process. First, we have the specification. Responsible for that is the 3GPP. And so it's an organization of different partners. And for example, the ETSI is a partner. And because of the ETSI is a partner, all members of the ETSI also are basically part of the 3GPP. The specification and also the standard is several thousand pages long, and the functions are defined over several documents. It's quite scattered across the documents. And those documents also define the security requirements and their implementation. When it comes to the next step, for example, the vendors uses a specification and implements it. And by doing this, for example, a developer sets down, uses the documentation or the document and interprets them. And this interpretation can lead to security errors as well. Finally, and we have here some operators also in the audience, I guess, the operators take the implementation of one of those big vendors and try and need to configure them and roll out them. And also this configuration can lead to serious problems and security flaws, which we will see later. It is also important to note that once a problem in the specification occurs, it is inherited through all other steps. So it is hardly possible to fix any specification flaw in the deployment itself. And sometimes you need to wait a generation, so for example, 10 years, that actually the next generation improves on the security of the known vulnerability. Now we have defined the life cycle. So how can we order today's topic in the relation of this life cycle? The challenge I'm going to address today in terms of V2X are related to the specification. What is the fundamental problem that we have when we have V2X deployed on top of a 5G network, and how is it solved? For IoT, I will go into the implementation and deployment. In particular, we will address the problem here when you are trying to run a campus network, what kind of implementation you want to select and how can you deploy it and roll out it securely. The selection does not mean that there are no implementation and deployment flaws of V2X in the implementation and deployment. It's just a selection for the today's talk. So next, we will address the challenges, the security challenges in V2X. So in a classical cellular network, the cell phones, so your smartphone, have a radio connection to the base station and a core network. The network itself serves as security anchor. An initial AKA protocol with symmetric keys are used for an initial AKA protocol for authentication and deriving keys for encryption and integrity protection. Precisely, it means that, we are here at a former smart card workshop, that your SIM card also stores the symmetric keys and performs the authentication in the initial process. So now let's replace our smartphone with cars and infrastructure systems. Let's take 2 cars here and also 1 traffic light. The traffic light should be your normal use case. The traffic light signal the cars its current status, whether it's green or red. And the problem here is that the whole communication must go over the base station or uses the base station. This leads to high data rates at the base station and also higher latency. And the base station might be also a single point of failure. If this fails, then important traffic information are no longer be transmitted. So to counteract this problem, the 3GPP people came up with this clever solution. Vehicles are now communicating directly with a radio link over the so-called side link protocol without the base station. So the problem is fixed. You have high data rates and you can decrease the latency, and the base station is not any more involved in the communication. However, by this fundamental shift to the new architecture, that means that the trust anchor in the core network is kind of omitted. We cannot rely on the core network connection for basically deriving authentication for all these entities in the net. The question now here is how can road users or vehicles exchange information securely even if the trust anchor of the network is eliminated. So a typical scenario that we would have is, for example, you have a traffic light that wants to inform an approaching car about its current status. In our case, the light is red. So in addition to the current status, other information like the current position are communicated to the car. So as soon as the car approaches, the traffic light sends the current status, and it's important that the traffic light signs the message so it cannot be forged or faked by any attacker. As soon as the car receives the message, it checks the signature and processes it, and comes probably to halt. In our use case, we assume that the traffic light and car do not know each other on beforehand. And in addition, we cannot use the network infrastructure to exchange key or verify some certification chains. What we want, but what we want here is that the messages are authenticated without the infrastructure during the act of verification. So, and this is particularly important because otherwise, yeah, some bad things can happen. For example, we don't want that an attacker basically stands inside of a highway when we are driving with like 130 kilometers per hour and just, yeah, you switch on a red light and spoofs the red light. In those cases, for example, our car will make an emergency stop and probably cause an accident. So the solution the Sidelink protocol relies on is based on cryptographic protocols, which are based on identity-based cryptography. So what is Sidelink and crypto-based or identity-based cryptography? In contrast to the classical public key approaches or certificate hierarchies, the traffic light in our example do not generate the private key by itself. Instead, a central instance, the private key generator, is used to generate a private key which is sent to the traffic light. Based on the master key, this key is derived and also known in the whole system, for example, at the car, public parameters are distributed. So that means the car has later the information which needs to verify the message. As soon as the car approaches, the traffic light signs a message with the help of the generated private key and sends the message, so the signature, to the car. The car can now generate the public key based on the public parameters and the identity of the traffic light, in our case, traffic light 123, and now also can verify based on the public key the message itself. So it knows, okay, comes it from the original traffic light. So this system has certain advantages over classical certificate hierarchies. In our case, offline verification, so without a contact of the network, and the message can be just verified on the identity and the public parameters. Still, there are open research questions in regards of the specification we are currently working on. For example, against which kind of attacker model, so what are the capabilities of attacker, this kind of scheme prevents. So which kind of attacks this prevents. So for example, what happens if the attacker has access to the public parameters, or what can he do if he is able to generate an own private key by the by the key generator. So next, so once we finish these V2X, I would like to go on to the challenges of 5G and IoT security. So because we know the field of IoT is huge, we first need to define which kind of IoT we are talking about today, and I need to scatter this down a bit. So let's assume you have a German-wide sensor network in a wide area deployment like the whole Germany with low data rates. For this, you can use existing 5G or more LTE networks of the existing operators like Deutsche Telekom, Vodafone, and O2. And here I would like to point you to two particular specifications, namely narrowband IoT and LTE-M, which are sub-specifications and allowing those your quality of service requirements for small sensor. Today, we are not going to talk about those. Today, we are going to talk about campus network. Imagine you have decided to, or you want to connect a factory. So let's say you have decided you want to deploy a campus network that can handle high data rates and also critical data. So what do you need to consider? Because you have realized that you are an operator of a 5G network. So you basically do that what the big operators do, but on small scale. What kind of hardware do you need to select, and what kind of software do you need to operate? How to configure them? For example, there are many choices. One of them are, for example, do you need to integrity protect your user data? So in public networks, the user data, so your actual IP data, is not integrity protected due to battery drain and power consumptions. So, but maybe this is something you want for your campus network. And I will show you, or I will shortly walk you through this process of making your campus network more secure. So on the left side, we see the life cycle again, which we have in the beginning. The good news up front is that the campus network, as you as a campus network operators, do not have to worry about the specification that much. So you don't need to get involved in the specification process at all. You should roughly know about it, what's in there, and maybe what are the security parts of it, but you don't need to get involved. This is the 3GPP. So, but what you should care about the implementation, that doesn't mean that you have to implement it by the specification by yourself, but you want to select secure components. So the question we are answering today is, what do you need to consider when selecting components regarding their security? And here it should be something useful like having a certificate or even an auditing scheme already in place. And we have heard this a lot today. Yeah. Besides the challenge of implementation, you also need to consider the deployment, right? You need to configure it and deploy it and maintain it. So also here, we're going into detail how to securely configure a campus network. So coming to the first point of secure component and their selection. So this GSMA, which is the industry association of mobile networks operators, and the 3GPP are developing a system for security testing and security auditing. This team is called NESAS. NESAS stands here for Network Equipment Security Assurance Scheme, and NESAS is split in two parts. So first of all, NESAS defines a product lifecycle of secure implementation at the network vendor. So, for example, this lifecycle is also auditing by some auditing companies in regards of the GSMA, and you find a list online which companies or which vendors have an audited lifecycle for which equipment. The other part is the security auditing and security testing. So it is possible that based on the NESAS and SCAS documents or 3GPP documents, that a certification authority basically gives a kind of check mark to a particular equipment based on this security testing and auditing. So also the security testing is split in two parts. So there's the general security testing. For example, if a device boots up from an unknown USB stick, and the other part is the specific security testing, which is particular for a protocol which is implemented in this entity. For example, what security algorithms are used with what priority? So if you are a 5G network operator, for example, in a campus network, a component that has a NESAS accreditation can already give you a first indication of what kind of component or what kind of security level this component has. So not only that the 3GPP and GSMA deploys NESAs, we are currently in the phase in turning this accreditation scheme into an official certification scheme. So the BSI is currently working on a pilot phase for the NESA CCSGI, where CCSGI stands for Cyber Security Certification Scheme German implementation. And this is currently in the pilot phase. So this basically puts a lot more weight into this kind of scheme. But it's important to note that both procedures are low assurance schemes. So there is a testing, but often it also relies on manufacturers or vendors' declaration. So, and there's also the effort to make this a European standard. So once we have selected a secure component, we need to configure it. Even the big operators have a problem, or we have seen big operators having problems in configuring their network securely. For example, we found that commercial network operators did allow no encryption and no integrity protection in their network. So data can be intercepted or even manipulated. I just recently looked at a configuration file of a core network component that had more than 6,000 lines of configuration, right? And so the problem is that this configuration is a dynamic configuration, more like a programming language. So a command in this configuration file that is listed after each other might override a previous statement. And so you cannot be sure which configuration is actually in place for this particular equipment. So imagine we have deployed a secure base station and we now need to configure it. So and verify if the configuration is secure. What helps here is kind of pen testing and basically test the network from the outside and to see if it's really secure or the security parameters are as expected. So the problem we see here is that pen testing in this kind of area with the protocols of mobile networks is not very well established, right? So we see a lack of tooling in mobile network pen testing. And we have noticed that even big operators do not have the skill set to test their own configuration to that extent. So what we need is basically tooling and education. And so I'm really happy to announce here today that we are currently spin-off a company that focuses solely on our mission to secure mobile networks. We focus on the security assessment of network equipment and configuration, and we want to make the tools and knowledge accessible for everyone that runs a campus network. So thank you much for your attention, and I would be pleased if we continue to stay in contact